All right, let's look at the difference between molecular and ionic compounds. All right, what we're going to be looking at in this first part is the difference between molecular and ionic compounds, and specifically be looking at differences in their bonding and their properties. So I'm going to back up a little bit and say this study guide number 4 is seemingly, I guess in some ways, the study guide is about nomenclature. All right, and nomenclature means a naming system. All right, so it's about learning how to name different kinds of compounds. But underneath that, the reason that nomenclature is really important is that nomenclature is also related to classifying different compounds. Different types of compounds have different naming systems, and so in order to name them properly, you have to be able to look at a compound and tell what kind of a compound it is. And understanding what kind of a compound it is tells you something about its properties. And so while we're going to be looking at naming, what we're really, let's say, almost a more important part of this is understanding the bonding schemes and the different kinds of properties of different compounds. And we're going to look at covalent and ionic compounds in here. We're also going to be looking ultimately at acids and organic compounds. So be thinking about this as we go through this. A big part of this is understanding different kinds of compounds and how those different kind of compounds are put together and how those different kind of compounds behave. Okay? And going back to kind of a running theme in this course, we define the difference between molecular and covalent compound, or excuse me, covalent and ionic compounds. Right? Molecular and covalent are synonyms, essentially. The difference between the covalent compounds and the ionic compounds is defined by their bonding, and the bonding, of course, is part of the microscopic representation, right? Because that's how they're put together on an individual molecular level. And one of the things that we want to understand is how the different way that the molecules are constructed, those microscopic binding properties, how those influence the properties that we actually see in the molecules, and those, of course, are part of the macroscopic representation. Right. So what we're trying to get at ultimately, as always, underneath the nomenclature part, is understanding the relationship between the microscopic and the macroscopic. All right, so first let's look at ionic compounds. Ionic compounds are those that are composed of two ions, a positively charged ion, a cation, and a negatively charged ion, which is an anion, right? And those things are combined together to make an ionic compound. So for example, sodium chloride, the way this forms is a sodium ion transfers an electron to a chlorine atom, and that losing that electron gives the sodium a positive charge, and gaining an electron gives the chlorine a negative charge, and so you end up with a cation and anion pair, and that is your ionic compound, those two things together. Right? And so the compound is really just held together then by these electrostatic charges. You've got a positively charged species over here and a negatively charged species over here, and because opposite charges attract one another, the attraction between that positive ion and negative ion is what holds it together. And Sometimes we call those ionic bonds, although they're not really a bond in the true sense of the word. It's just an ionic attraction is probably a better word for it. And so on the microscopic level, what these look like is you get a large number of positive charges, the sodium ions in this case, and a large number of negative charges, chlorides, right? And they make this extended array of positive and negative charges. One of the things that's important here is if you look at this, there are no individual sodium chloride units. You just have this large three-dimensional array, right, of positive ions and negative ions, and you can't really identify. Let's see if I guess this is a good color. You know, you wouldn't really say that's one molecule and that's another molecule, right? It's really just a large collection of positive and negative ions all attracted together by that electrostatic force. Okay, and so that allows them to form crystals, and in the macroscopic state, when we see these crystals, we see them as things like this. This, of course, is table salt. Most ionic compounds look kind of similar to this. They might be different colors. Copper sulfate is really kind of a pretty blue color. A lot of the transition metals form ionic compounds that have really nice, pretty colors, purple and green and orange and things like that. But generally speaking, ionic compounds, because they have positive and negative charges, they form these nice crystals, right? And so in the macroscopic state, they'll appear as crystalline solids. All right. Now, if you're just looking at the formula of a compound, how can you tell whether something is likely to be an ionic compound or a covalent compound? So we need to be able to look at them and understand what makes the ionic compounds. And ionic compounds, of course, are formed between a positive ion and a negative ion. The most common way for that to happen is a metal forming the cation and a nonmetal forming the anion. And we looked at the periodic table in the last section, and so you know that the metals are all over here. And the nonmetals are over here. And hydrogen, and we always have to keep an eye on hydrogen because he's tricky, right? Hydrogen, even though it's on the left side of the table, hydrogen is a nonmetal. So for the purposes of this stuff, we should think of it as being over on the left with all of these guys, like carbon and oxygen and chlorine and bromine, and so on and so forth. So the first type of ionic compound are ones that are formed between metals and nonmetals. So examples of this would be things like a compound between, say, sodium and chlorine that we were talking about before, right? Sodium chloride, right? Or maybe potassium and oxygen, right? We'll talk about these formulas later, where that 2 comes from. Or, again, maybe something like, well, let's go into the transition modes. Maybe something like cobalt and bromine. So you might have something like cobalt bromide, right? These are all things that would be considered ionic compounds, and we recognize that because we've got a cation, a metal over here forming a positive ion, and a nonmetal over here forming the anion. Another way to make an ionic compound is with polyatomic ions. And in the study guide, there's a list of polyatomic ions. You should work on those and start memorizing those, since it's just basic knowledge, the base of the Bloom's taxonomy pyramid. A good way to learn those symbols and charges and names of the polyatomic ions would be just to make some flashcards. So first thing I would say is I would recommend making some flashcards with the name on one side and the formula and charge on the other side. It's going to be really important that you're familiar with all of those polyatomic ions on that sheet. All right. So you can form a ionic compound where you have a polyatomic ion substituting for the anion here. So you could have a sulfate, which is negatively charged ion. You could have that substituting for the nonmetal like the chloride or the bromide or the oxide or something like that. You have a metal for the cation and a polyatomic anion for the anion. You can also have, there are a few, not a lot, but there are a couple of polyatomic cations. Ammonium ion is one of them. Right. So you could have an ammonium ion for the cation and something else for the anion. So for example, you could have ammonium ion as your cation and chloride, typical nonmetal, for the anion. And so you can have a ionic compound of ammonium chloride. Right? And notice again, like we said last time, you know, these are all made of positive and negative ions, so they make these really nice crystals. And you can see the macroscopic appearance of all of these is a crystalline solid. All right, so we said before that one of the things we wanted to be thinking about is the relationship between microscopic and macroscopic representations, how the particular bonding structure corresponds to or causes, I guess I'd say, the macroscopic properties that we see. Right? So for all of these ionic compounds, they are a three-dimensional array of positive and negative ions. Right? This electrostatic force is a fairly strong force. It forms an attraction between all of them. But, and this is kind of important, there are no discrete molecules, right? So we wouldn't say that that's one molecule there and that's one other molecule here. It's really just one big array of positive and negative ions. And so what we see with ionic compounds is, first, that because of that strong electrostatic force between all the ions, they have very strong intermolecular forces, which holds all of the ions together. And so ionic compounds are essentially always solids at room temperature and generally have very high melting points, 500 degrees Celsius or higher. A lot of them, sodium chloride, I think is somewhere around 800 degrees Celsius. You really got to get them hot in order to melt them, right? They also have very low vapor pressure, and we'll talk about vapor pressure more in the second semester, but basically what vapor pressure means is the ability of molecules or particles to escape into the gas phase. And if the attractive forces between the particles are weak, then it's easy for the molecules to escape off into the gas phase. But if the attractive forces between them are strong, then they can't escape, and so everything's going to stay in this solid. All right, because ionic compounds have strong attractive forces between the particles, very few molecules or ions get into the gas phase, and so they have a low vapor pressure. One of the ways you can see that in the way you experience things is that something that has a high vapor pressure with a lot of molecules in the gas phase can very often have a strong odor. But things that don't allow molecules to get into the gas phase, if nothing's in the gas phase, then it can't possibly have an odor. Right? So you notice salt has a distinct taste, but it doesn't have a smell. and that's because it has a very low vapor pressure, and there are no salt particles getting up into the gas phase. All right. And the last thing is that even though ionic compounds can be either soluble or insoluble, I'd say probably most are soluble. I think that's probably a good statement. Many are not soluble, most are. The important thing is, if they are soluble, the ones that dissolve in water conduct electricity, right? Or their solutions, I should say, conduct electricity. And the reason for that is, if you take this salt here, right, this ionic compound, and dissolve it in water, if it dissolves, then all of these particles, the cations and anions, all separate in water, right? They don't stay together as a unit. The cations and anions separate, and so you end up with a solution that contains a whole bunch of positive and negative charges, and because it has positive and negative charges, it can conduct electricity. Right? So that's a very big difference between ionic compounds and molecular compounds. All right, so molecular compounds, or covalent compounds, right, are molecules that are held together not by transferring an electron from one atom to another to make ions, but by sharing electrons. Right? So, for example, hydrogen and fluorine, hydrogen and the fluorine each share an electron, and those electrons form a bond between them, and so you get this molecular unit, and that shared pair of electrons. It's called a covalent bond. Right? And if you look at a bunch of, hydrogen fluoride is actually a gas at room temperature, but if you cool it down enough to make it into a solid, right, you could make solid hydrogen fluoride. Right. It would look basically like this, right, where all the particles are condensed together tightly into a solid crystal, right? But unlike with the ionic compound, you actually do have individual identifiable molecules. They say, here's a hydrogen fluoride right here, here's a hydrogen fluoride right here, here's a hydrogen fluoride right here, right? Instead of having just a collection of positive and negative ions, you actually do have individual, discrete, identifiable molecules, right? And that's a difference, an important difference between ionic and covalent. In fact, and that's why we call them molecular, because they retain their molecular identity as individual molecular units. All right, so if we're just looking at formulas, like H2O or something like that, and we're trying to determine whether something is an ionic or a molecular compound, again, we can look at the periodic table, and molecular compounds are formed from combinations of two or more nonmetals. And we remember from the periodic table, we were looking at a while back, nonmetals are these guys over here. And actually, I'm going to extend this a little bit. I would include metalloids in this group for identifying molecular compounds. So nonmetals or metalloids in combination with one another form covalent compounds or molecular compounds. And remember, again, also with hydrogen, We should think of hydrogen as being over here, even though it's on the left side of the table, it's a nonmetal. So anytime we form a compound using these elements, right, then the compound is going to be molecular or covalent, right? Just two synonyms for the same thing. So some examples of things that you might be familiar with. Carbon dioxide, people talk about that a lot in terms of the atmosphere and global warming. Water is a simple one, right? Water is a molecular or covalent compound. If we made a compound with phosphorus and chlorine, phosphorus trichloride, that would be a covalent molecular compound, right? Sugar, right, is covalent. And let me throw one in from the from these metalloids, something like arsenic trichloride, right? Here's arsenic here in the metalloids. That would also be a molecular compound. All right, so let's look at the microscopic and macroscopic properties of molecular compounds. All right, as we said before, unlike ionics, they exist as individual discrete molecules. Right. Right. So if we have a bunch of HF, a bunch of hydrogen fluoride, they're going to be distinct hydrogen fluoride molecules rather than a random collection of hydrogens and fluorides. Right. And what's important about these is that covalent bond here in the middle, right, is a very strong force. That's what keeps them together as discrete molecules so they don't break apart into ions, right? And this force, remember, we talked some time ago about intramolecular forces. Right? Intramolecular forces are forces within the molecule that hold the molecule together. And intermolecular forces are those that are between the molecules. And for molecular compounds, the situation is almost the exact opposite as it is for ionic compounds. For molecular species, they have very strong intramolecular forces. So these bonds within the molecule are very, very strong, but relatively weak intermolecular forces. So the forces between the molecules are fairly weak, right? So each molecule is held together as a unit very, very tightly, but the molecules are not held together as tightly as a group, right? And so let's see what that does for the properties. Okay. So since the attractive forces between the different particles, the intermolecular forces, are not as strong, they're not always held together tightly as a solid. So depending on the composition of the compound, they can be either a solid, a liquid, or a gas. And if they are a solid, the solids very often have fairly low melting points. So it's fairly easy to heat something up a little bit and convert it from a solid to a liquid, or heat it up a little more and convert it to a gas. Also, because the intermolecular forces are weaker, it's easier for the molecules to escape off into the gas phase since they're not held as tightly. And that means that molecular compounds are going to have a higher vapor pressure, right? More molecules escaping off into the gas phase, and that means that very often covalent compounds have a strong odor. Right? A good example of that is this compound. Now here's an example here. This is isopropanol. Right? You can buy it in the store. It's the name rubbing alcohol, right? And this is the stuff that the doctor or a nurse puts on a little cotton swab and wipes on your arm before they give you a shot. And you know, as soon as they open that bottle and put on a little cotton swab, you get that smell instantly. And you can smell this isopropyl alcohol. It has a very distinct smell. And you know, oh, I smell that smell, I know I'm about to get a shot, right? Anyway, the fact that you can smell it means that this compound has a high vapor pressure. The molecules are escaping into the gas phase very quickly. Gasoline also. Gasoline is a mixture, not a compound, but many of the compounds in gasoline, actually I guess all of the compounds in gasoline are molecular compounds. And so the compounds in gasoline also have a high vapor pressure. And that's why when you're at the gas station filling up the tank, you definitely get a whiff of that gasoline going in there. Okay, and then unlike ionic compounds, covalent compounds might be soluble, might be insoluble, but if they are soluble, the solution does not conduct electricity, because when it dissolves, instead of getting a bunch of ions in solution, you just get a whole bunch of individual neutral covalent molecules floating around. Sugar is a good example. Sugar is very, very soluble, but you put sugar in water and you just get a bunch of sugar molecules floating around. There are no ions, and so the solution can't conduct electricity. All right, let's do a couple quick sample problems to show you what to expect from this section in the study guide. So I'll give you a couple of examples of different element combinations, and you should predict whether the compound will be an ionic compound or molecular compound. So we could try sodium and fluorine, or sulfur and oxygen, or phosphorus and hydrogen, or copper and bromine. All right, the key to answering these, of course, is going to depend on looking at the periodic table. I'll put that here. It might be a little small for you, so if you need to get one, if you need to get your textbook out or something to look at a periodic table, there, go ahead and do it. Take a minute, hit pause, look at these groups of ions, and try to identify them as ionic or molecular, and then I'll show you what I've got. Okay, so let's take the first one, sodium and fluorine. All right, sodium is over here, and fluorine is over here. All right, sodium's on the far left, that's a metal. The fluorine is in the upper right, that's a nonmetal. So because we have a metal and a nonmetal, metal and a nonmetal, a compound formed from sodium and fluorine is going to be ionic. Okay. Next, let's try sulfur and oxygen. Sulfur is right here, and oxygen is a neighbor. All right, they are both on the left-hand side, the upper left. Right, so a combination of sulfur and oxygen is going to be a nonmetal and a nonmetal. So that would be a molecular compound. And again, I'm using molecular and covalent as synonyms here. All right. Let's see. Phosphorus and hydrogen. Phosphorus is here. Hydrogen is here. And even though hydrogen is on the left, right, remember that hydrogen is actually a nonmetal. So this one is also a combination of a nonmetal and a nonmetal. So this is a molecular compound. And then finally, copper and bromine. Let's see, copper is a transition metal. It's right over here. And bromine is over here. All right. We got our metalloids going through here. So copper is a metal and bromine is a nonmetal. If we have a combination of metal and nonmetal, then this is going to be ionic. Right. So we've got 2 ionic compounds and 2 molecular compounds. Okay. And based on that also, we should be able to predict some of the properties of these species, right? 2 of them, without knowing anything else except for the composition of them, 2 of them here, we could say we already know that those 2 things are solids, right? Just because they're ionic. If either of these have any kind of an odor, it would be this one and this one. The 2 ionic compounds can't have an odor because they have such a low vapor pressure. Okay, let's try another one. Okay. We've got a list of, let's see, we're going to look at 4 different compounds. Lithium chloride, carbon tetrachloride, iron oxide, and calcium sulfide. And the question is, only one of these is a liquid at room temperature. Which one is it? All right. Well, we know that molecular compounds could be either liquids or solids, but ionic compounds are always going to be solids. So if we can identify the things that are ionic, we can rule those out as liquids at room temperature. So lithium chloride, take this first one here, better color, lithium chloride, right? Lithium is over here, and chloride, or chlorine I should say, is over here, right? So lithium chloride is going to be an ionic compound because we've got a metal and a nonmetal, right? Carbon tetrachloride, carbon is over here, and chlorine again is over here, right? So that's 2 nonmetals. That means that carbon tetrachloride is a molecular compound, right? So that could possibly be a liquid at room temperature. Okay. Iron oxide. Iron is here. It's a transition metal. And oxygen's over here. That's a nonmetal. So I've got a nonmetal and a nonmetal. That means that this one is going to be ionic. All right, that one's ionic. And cadmium sulfide. I'm sorry, not cadmium sulfide, calcium sulfide. Right? Calcium is over here. That is an alkaline earth metal. And sulfur is over here. That's a nonmetal. So we've got a metal and a nonmetal. So that's a calcium sulfide is going to be an ionic compound, right? So if we're looking for something that's a liquid at room temperature, we know it can't be calcium sulfide, can't be iron oxide, can't be lithium chloride. The only one that could possibly be a liquid at room temperature is carbon tetrachloride, because that's the only one that is a molecular compound. Also, if I said one of these has a strong odor, which one is it? The only one that could have an odor is going to be also carbon tetrachloride, and it does in fact have a pretty strong odor. It's also carcinogen, so you don't want to smell it any more than you have to. Okay, so what we looked at in this video, we're looking at 2 types of compounds, ionic compounds and molecular compounds, and we'll use these 2 terms, molecular and covalent, as synonyms, right? An ionic compound is one that's formed from a combination of a cation and an anion, whereas a molecular compound is something formed by two atoms or more atoms, right? Two or more atoms joined together by a covalent bond in the middle. And these are going to have a very strong intramolecular force, but fairly weak intermolecular forces. And the opposite is going to be true here for the ionic compound. All right. So we looked at the bonding for each of those, which I just mentioned a minute ago. We talked about how to determine based on periodic table, which kind of elements are likely to form ionic compounds and which things are going to form molecular compounds. So by looking at the formula of a compound or the elements that it contains and then looking at the periodic table, you should be able to predict whether something is a molecular or ionic compound. Right? And then finally, if you know whether something is molecular or ionic, you should be able to predict some, not all of course, but you should be able to predict some of the macroscopic properties of those substances based on whether they are ionic or covalent. Okay, great. And the next one we're going to start looking at nomenclature. Once we can, now that we are at the point that we can distinguish between different kinds of molecules, we can start looking at the rules for naming them. So that will be next.